If I asked you to imagine the biggest tech disaster in history, your mind probably goes to something like Chernobyl, right?
Hmm?
Or maybe a massive blackout.
Sure, something man-made.
Exactly. But what if the disaster started with just an astronomer looking through a telescope on a totally normal day?
And that single observation, it kicked off what became, well, the most intense geomagnetic storm we've ever recorded.
An event so powerful it literally made the sky glow red over the tropics and turned the world's most advanced tech at the time into a sparking, dangerous mess.
That's the Carrington Event. And the sources we've been digging into for this deep dive, they just paint this incredible picture. It's both this unbelievable historical moment and, frankly, terrifyingly relevant.
So that's our mission here. We want to unpack this whole thing. It peaked back on September 1st and 2nd, 1859. Yep, during solar cycle 10. We're going to look at the bizarre impacts, the first-hand accounts, and then pivot to the really critical question. What would a storm like that do to our world today? Because the risk is in the trillions of dollars.
Multi-trillions. And we even have some new data that suggests the 1859 event was even stronger than we'd been modeling.
Okay, so let's start at the beginning. The source. This was a massive coronal mass ejection, a CME, shot off from the sun.
Right, and aimed directly at us.
But CMEs usually take a few days to get here.
Yeah.
What made this one so incredibly fast?
That's maybe the first unbelievable detail. I mean, a typical CME takes, what, maybe 3-4 days to travel the 93 million miles to Earth?
Something like that.
This one did it in 17.6 hours.
17 and a half hours. That is just... It's an astronomical bullet. How is that even possible?
Well, the leading theory is really compelling. It seems like a previous CME, one that happened a couple of days earlier.
The one that maybe caused that first round of auroras on August 29th?
That's the one. That first wave acted like a snowplow. It just, cleared out all the ambient solar wind, all the plasma that was in the way.
So it paved the road.
It paved the road. So when the main, much more powerful CME erupted on September 1st, there was just far less resistance. It could travel at this record-breaking speed.
And that timing, it leads us to a huge scientific first. Because this wasn't just felt on Earth.
No, it was seen for the very first time.
Right, on September 1st, 1859.
18 a.m. Greenwich Mean Time. You have two British astronomers, Richard Carrington and Richard Hodgson, working independently.
And they're just doing their daily observations of sunspots.
Exactly. And they both, at the same time, see the sudden, intense flash of white light from a sunspot group. They had just recorded the first ever visual observation of a solar flare.
And then less than 18 hours later, all hell breaks loose on Earth. That's a pretty undeniable link.
It is. But they actually got evidence even sooner than that. Instantly, in fact.
What do you mean? At the Kew Observatory, a Scottish physicist named Balfour Stewart was watching the magnetometers. And right at 11:20 a.m., just as the flare was seen, the needles jumped.
The needles jumped. He recorded a sharp fluctuation, something we now call a magnetic crochet.
A magnetic crochet.
Yeah, it's a very specific signature. The intense X-rays and UV radiation from the flare hit our upper atmosphere. They ionize it, change its conductivity, and that makes the Earth's magnetic field ripple, instantly.
So Carrington sees the light, Stewart sees the magnetic ripple.
And Carrington himself suspected the connection. He was cautious, of course. He famously wrote that one swallow does not make a summer.
A classic bit of scientific understatement. But what followed was, well, it was a summer of light for the entire planet. Let's talk about what people actually saw. The auroras.
Oh, the accounts are just breathtaking. I mean, these are lights that are normally confined to the poles.
Right up north, way down south.
During this event, they were seen down to south-central Mexico, Cuba, Hawaii, Colombia. People saw them in southern Japan and China. We have reports from New Zealand.
So for most people on Earth who saw this, it would have been their first time. A completely alien experience.
Completely. And the brightness was just off the charts. You have these stories of gold miners in the Rocky Mountains.
This is my favorite one.
It's incredible. They wake up in the middle of the night because the glow is so bright. They genuinely think it's morning and start making breakfast.
Just imagine that. No context for it, just the sky is on fire.
And in the northeastern U.S., people reported being able to read a newspaper just by the light of the aurora.
We pulled this great quote from a Baltimore newspaper at the time.
Right, the Baltimore American and Commercial Advertiser.
And they said the light was greater than that of the moon at its full. They talk about this beautiful as well as singular appearance over the quiet city. It sounds beautiful, but also eerie.
Deeply unsettling for many. There's this fantastic letter from an Australian gold miner, C.F. Herbert, writing about it 50 years later.
What did he say?
He talked about the almost unspeakable beauty, lights of every imaginable color. But he also made this really sharp point about how people reacted.
The rational versus the superstitious.
Exactly. He said the rationalists saw nature in her most exquisite robes, but the superstitious saw dire forebodings. They thought it was a sign of Armageddon.
A profound psychological moment.
Mm-hmm.
But okay, while the sky is putting on this show, something physical is happening down on the ground.
Yeah.
Something that's directly affecting our technology.
Right. This is where we shift from the light show to the physics, to the telegraph network.
Which was the internet of its day.
It was. And the geomagnetic storm created these massive geomagnetically induced currents, or GICs. They flowed through the long copper telegraph wires and just overloaded everything.
And it wasn't just that the lines went dead. It was violent.
Oh, very. Operators were getting powerful electric shocks from their equipment. Telegraph paper was reportedly catching fire.
Sparks from the pylons.
Right. The system was literally burning out from electricity induced from space.
Which leads to the most incredible detail of this whole event, the moment that just perfectly captures the raw power.
The battery-free conversation.
Running on pure auroral current.
It's amazing that we have it documented. It happened on the line between Boston and Portland, Maine, on the night of September 2nd.
So what happened?
The Boston operator realizes the current from the storm is so strong and so steady, he has an idea. He sends a message to Portland.
And says what?
He asks them to disconnect their batteries completely, just run off the line.
And they do it.
They do. And Portland sends back a message saying the signal is actually better than with their batteries on. They noted the current comes and goes gradually, and they worked like that for 2 hours.
Sending and receiving normal commercial messages.
For 2 hours, powered entirely by a solar storm.
It's just incredible. But let's pause there. That was 1859. A few sparks, a few shocked operators. Now we have to ask the big question. What would a storm of that magnitude do to our world today?
The vulnerability is, it's on a completely different scale. It's almost incomparable.
Because back then, the only long conductors were some telegraph wires.
Exactly. Today, our entire civilization is built on continents laced with high-voltage transmission lines, thousands and thousands of miles of them.
So a repeat event wouldn't just be a disruption.
It would be catastrophic. We're talking widespread, long-term blackouts. And not just blackouts, but permanent damage to the grid itself. We got a tiny preview of this in March 1989.
The Quebec blackout.
Right. A much, much weaker storm than Carrington knocked out power to millions in Quebec for 9 hours.
So let's get into the mechanics. How does this induced current from space actually kill a modern power grid? We're not talking about sparks on a wire anymore.
No, we're talking about melting down the core components of the grid. It's because the GIC, this current from space, is basically a direct current, a DC current.
And our grid is all AC, alternating current.
Precisely. So this rogue DC current gets into the massive high-voltage transformers. It flows through their ground connections and pushes the transformer's magnetic core into saturation.
Which is a state it's absolutely not designed to be in.
It's catastrophic for it. The core overheats, the windings can be irreparably damaged, and the whole unit, this massive city block-sized piece of equipment, can physically burn out.
And you can't just, run down to the store and get a new one of those.
Yeah. Not at all. These things are strategic assets. They weigh hundreds of tons. They're all custom built, and the lead time to get a new one is often over a year, maybe 18 months.
So if you lose dozens or hundreds of them at once,
the grid is down until they can be replaced, not for hours or days, for months or even years.
And we came frighteningly close to testing this theory out for real, didn't we?
We had a huge near miss. On July 23, 2012,
The storm that missed.
a solar superstorm, measured to be at least as powerful as Carrington, erupted from the sun.
Yeah.
But its trajectory just happened to miss Earth's orbit.
By how much?
By about 9 days. If we had been in that spot in our orbit 9 days earlier, it would have been a direct hit.
Wow. Okay, let's talk numbers. The financial cost? What did the big Lords of London study project?
Their 2013 research was sobering. For the U.S. alone, they estimated the cost at between $600 billion and $2.6 trillion.
And if you adjust that $2.6 trillion for today's money,
you're looking at close to $3.5 trillion, and that's just the direct cost. Grid replacement, business losses.
the indirect costs seem even worse. You've mentioned the food supply before.
The indirect impacts are where it gets really terrifying. Think about modern agriculture. It runs on industrial inputs, especially nitrogen fertilizer,
Right, the Haber-Bosch process.
which requires enormous amounts of stable, continuous electricity. If the grid is down for months, fertilizer production stops. Day one.
And the impact on crop yields.
The projections are dire, a global yield loss of somewhere between 38 and 48%. In heavily industrialized areas like Central Europe, it could be up to 75%.
That's a global food crisis.
It's a multi-year economic and humanitarian crisis that stems directly from the electrical grid going down.
And just to make this all a bit worse, we now think the 1859 storm was even more violent than those models assumed.
Yes, that's what this new 2024 analysis showed. They went back and digitized the actual paper magnetogram readings from 1859.
From the Kew and Greenwich observatories.
Right, and they could calculate the rate of change of the magnetic field, which is the key metric.
And what did they find?
They found field change rates of over 700 nanoteslas per minute.
Okay, give me some context. Is 700 NT per minute a lot?
It's huge. The modern 100-year extreme event that grid planners model for is around 350 to 400 NT per minute.
So Carrington was double our worst case scenario.
Essentially, yes. And it's that speed, that rate of change that matters. The faster the magnetic field changes, the higher the voltage it induces in power lines. So the destructive potential is far, far greater than we previously thought.
Okay, so 1859 was an absolute monster, the record holder. But if we look at the really long-term history of the Earth, was it the biggest the sun can do?
That is the critical question. And to answer it, we have to look beyond direct observation and into what we call historical proxies.
Because our magnetic records only go back a couple of centuries.
Exactly. So scientists look for isotopic signatures, specifically carbon-14 in ancient tree rings and beryllium-10 in ice cores.
How does that work?
Well, when a massive solar eruption happens, it blasts out these high-energy particles. When those particles hit our atmosphere, they create these specific isotopes.
C14 and B10.
Right, and that C14 gets absorbed by trees as they grow, and the B10 falls with snow and gets locked in ice. So by measuring the spikes in those isotopes, we can see when huge solar storms happened in the distant past.
And this has revealed these so-called Miyake events, storms even bigger than Carrington.
Far bigger. We have definitive proof of massive storms in 774, 775 CE, and again in 993, 994 CE.
And the 774 CE event was?
Potentially 10 or more times the size of the Carrington event.
10 times. It's hard to even conceive of that.
It really pushes the limits of what we understand about the sun, and there's even proxy data suggesting an even bigger event way back around 7176 BCE. It proves the sun has a capacity for violence far beyond what human civilization has ever experienced in the modern era.
And getting this science right is crucial, which brings up a bit of a controversy in the research, doesn't it, about the ice cores?
It does, and it's a great example of science correcting itself. For a while, some researchers were using nitrate layers and ice cores as another proxy.
The theory being that the solar radiation created these nitrate spikes.
Correct. But more recent work has cast a lot of doubt on that. They found that the spikes didn't line up globally. You'd find one in a Greenland core that wasn't in an Antarctic core.
So not a single global event.
Exactly. It suggests those nitrate spikes are more likely from localized terrestrial things like massive forest fires.
Yeah.
So now the field relies much more heavily on this C14 and B10 data, which is much more robust. This has been an incredible deep dive. To just try and recap the sheer scale of this, you have a solar flare that kicks off a CME that crosses 93 million miles in just 17.6 hours. It generates auroras so bright people literally start making breakfast. It allows telegraph operators to have a 2-hour conversation with no batteries at all.
And we now know it induced magnetic field changes 700 NT per minute that are double what our modern grid planners use for a worst-case scenario.
And if it happened today, we're looking at a multi-trillion-dollar risk. A risk of permanent grid damage that could shut down global agriculture and cause unimaginable societal disruption.
Which brings us to a final thought for you to take away.
If we connect all this, we know the sun has produced events, like in 775 CE, that were maybe 10 times larger than Carrington. So, given that historical fact and knowing that the physics of solar flares might share mechanisms with even bigger superflares we see on other stars, what does that tell you about the true maximum scale of space weather our planet might face? And are we remotely prepared for that ultimate worst-case scenario?
A question that definitely demands some global attention.